to start the next unit, which is on H and R parameters and their use in small signal amplifier analysis. What are small signal amplifiers? Small signal amplifiers are in which the signal strength is low as compared to the DC operating point parameters. You remember we said that the real objective of amplifiers is to amplify AC signals, and for proper application and proper operation of the amplifiers, we have to bias the transistor in the circuit properly, and the biasings which we use are that emitter junction forward biased, collector junction reverse bias. Then the operating point has to be chosen properly, and there should be a proper design for the biasing circuit. This was discussed in previous lectures. On these DC currents and voltages which we have set on the operating point, the AC signal which we want to amplify is superimposed. So, when we say small signal amplifiers, these currents and voltages AC part which is superimposed on the DC, they are small. AC part, AC current and voltages are small in comparison to the DC current and voltages which we have set at the operating point. So, these are small signal amplifiers, and the parameters and the analysis which we are now conducting, we are going to study, this is applicable only for small signal amplifiers. Large signal amplifiers, which are actually called power amplifiers, they are analyzed differently, and that we will see later. Now, for an amplifier, there are 4 most important parameters. These parameters are important amplifier parameters. One is the input impedance. Input impedance. You know that resistance and impedance, they may differ at high frequencies. When the frequencies are small, then resistance and impedance, they are very close to each other, and so we may call input resistance or input impedance, but it is better to call input impedance because frequency we are not yet defining. The other parameter is the voltage gain. Voltage gain of the amplifier. The third parameter is current gain. Current gain of the amplifier, and the fourth parameter is output impedance. Output impedance of the amplifier. So, remember these are the 4 important parameters, and they characterize small signal amplifiers: the input impedance, the voltage gain, the current gain, and output impedance. This we are going to estimate by using expressions, and expressions they will be based on 2 models which we are going to study. One is H parameter. H stands for hybrid parameter. H parameters. H parameters, and this H stands for hybrid. hybrid parameters, but popularly they are known as H parameters. And then after we finish this analysis, we will take another analysis which is through R parameter analysis. R stands for resistance parameters. So, first H parameters, hybrid parameters. Why this hybrid? These are called hybrid parameters, because before the invention of the transistor, there were in electronics, there were tubes, all circuits were designed in tubes, and tubes could be analyzed comfortably with two sets of parameters, any one of them, in fact, the impedance parameters, these are also called the Z parameters. All these four quantities for the circuit, amplifying circuit, could be obtained in terms of Z parameters, and then there were admittance parameters. And popularly these are called Y parameters. So, there were 4 Z parameters, there were 4 Y parameters, and they were able to define, to give the estimation of all the 4 quantities of interest, the 2 impedances, input and output, and 2 gains, the voltage gain and current gain. But when the transistor was discovered, was invented, then there was problem in defining, in measuring these parameters, either Z parameters or Y parameters for the transistor. So, then another set of parameters was developed, and that is known as H parameters. Now, H parameters are applicable for any 2-port network. This is 2-port network. This is port 1, this is port 2. Port 2, and here we are not concerned what is inside this box. We are concerned with the terminal currents and voltages. So, let this current be I1 and this voltage here be V1. Similarly, the current here is, let it be I2, and the voltage here is V2. Now, these currents and these voltages, they are total current and voltages, because as I have said earlier that in a amplifier the AC signals are superimposed over the DC. So, this is the instantaneous total values, total currents and total voltages. Now, our transistor fits in, that is also a 2-port device like this. Here is the transistor circuit. This is simplified circuit. Actual circuits we will be drawing. This is also a 2-port network. This is port 1 here and this is port 2 as it is here. So, Now, we will define first the H parameters, that we will take this very network. Let me redraw the network. The network is or this is just the transistor, and these are, this is I1, this is V1, and this is I2 and plus minus V2. The parameters can be defined by taking out of these 4 quantities the 2 currents and 2 voltages. 2 are taken as independent and 2 are taken dependent. So, we can write the fundamental relation for dependent variables. We take V1 and I2 as dependable variables. Then the functional relationship with other 2 parameters I2, I1 and V2 can be written, can be expressed like V1 is equal to F1 I1 V2 and I2 is equal to F2, the function I1 and V2. What these equations represent? They are representing that I1 and V2 are independent variables. The input current, for example, in a transistor, we can decide and we can choose whatever we want, and V1 will be dependent on I1 and of course, and I2 as we will see. Similarly, this equation tells the relationship, the dependence of I2 as a function of the variations in I1 and V2. For a small signal operation, for a small signal operation, changes in the voltage V1 and current I2 may be expressed as total differentials. And this is dV1, the total change in V1. This depends on this term, the first term. This is the rate of change of V1 on I1, and if I1 changes by dI1, then this gives the total change in V1 as a result of change dI1 change in the current, and this term is the change in V1 because of V2 when. So, this is the rate and this is the total change in V2, and hence this is the total dependence of V1 on I1 and V2. Similarly, we can write the another equation let us call this equation 1 and this as equation 2. And remember, we were talking about V1 as the total current like this. Here this was the DC current and voltage, and so this is, let us say in this case this is that voltage over which the AC signal, a small signal is superimposed. So, this is AC, this is DC. So, when we talk of variation, then this accounts for actually just the AC component. Similarly, here the AC component. Now, let us look at these derivatives. What do they represent? This delta V1 I1, you will recall that this has the dimensions of impedance. And this we will see, and so this we replace for the time being with the H parameter H11, hybrid parameter 1. Similarly, this quantity is a voltage ratio. So, this is represented by the quantity, the another H parameter H12, and this one as H21 and this one as H22. Now, this is not random. See 1 1, both quantities involved in H11 are from port 1, V1 I1. So, 1. Here it is 1 2. So, this is H12. Here the ratios are of current and two ports are involved, the output port and input port. So, H21 and similarly here H22. Now, these are the variables, the varying quantity, and what will vary? DC is constant, AC part will vary. So, taking this voltage, AC quantities we write with small letters. So, we write this as V1 and this we write as small I2, and then we can write these equations 1 and 2 like this. V1 equal to H11 I1 plus H12 V2 and I2 is equal to H21 I1 plus H22 V2. This we call equation 3 and this we call equation 4. Now, these equations are applicable to all the configurations of the amplifiers, whether it is common base, common emitter or common collector. These equations are valid, and in fact, the whole analysis which we are trying to study, they are applicable to all these circuits. And now, and these are the H parameters, 4 H parameters, and the hybrid nature of these parameters is again that will soon be clear. As I said that H11 has the dimensions of impedance. So, this is actually H11 is often written as H I. I stands for input impedance, so I for input, and so similarly this H12, this is a reverse voltage ratio. So, this is HR, R for reverse, and similarly H21, this is I2 by I1 under certain conditions, but this is written as HF, F for forward, and the fourth parameter H22 has dimensions of admittance. So, this is the, and both properties, both parameters involved in this are for the output port 2, and hence this is, as we will see, the output admittance. So, this is written as H O. So, 4 parameters, and the hybrid nature of these parameters becomes clear right now. For example, earlier in the beginning we talked about admittance parameters or impedance parameters. All the 4 parameters were either impedance parameters or admittance parameters. Here the hybrid nature becomes clear that this is impedance, H I is the impedance and H O is the admittance. So, impedance, admittance, and this is the forward current gain, actually the ratio of the two currents I 2 by I 1. You remember the fundamental definition of gain for any quantity is output quantity in the same quantity at the input, that gives the gain. So, I 2 by I 1 is the gain, the forward current gain, and this is a feedback term, reverse voltage ratio H R, and so these are the two, this is current ratio which is forward current gain, this is voltage ratio, and these are the impedance. So, that is why these parameters are called hybrid parameters. Now, let us define that what, under what terminal conditions these are measured and defined. The manufacturers almost for all transistors give the H parameters, and so this, let us define that H 11 which we have written as H I. This, if you look at this equation, if V 2 is 0, then we can define H 11 from here as the ratio of V 1 by I 1. So, this is defined as V 1 by I 1 under the terminal condition that V 2 has to be 0, V 2 is 0. So, I write in full, this is input impedance measured with output shorted or short circuited for AC. V 2 will be 0 only when this output is short circuited for AC. So, this is, remember these are very important. If this is not 0, then we can't define this input impedance by this ratio. This ratio will give, that also implies that if we change the terminal conditions, if we change this, then this will also change. So, that is not the motto. Motto is to find the value of H 11, and this is defined under the condition V 2 is 0. Similarly, we define other parameters H12, which is the reverse, and this is the ratio of here again from equation 3. If I1 is 0, then this ratio H12 comes out to be V1 by V2. So, V1 by V2 under the condition that I1 is 0. I1 0 means this is input current, and so this is reverse voltage ratio measured with input open circuited for AC. When this is open circuited, in a open circuit the current is 0. So, the input has to be open to measure this, and this is written as HR, and similarly H21, which is written as HF, and that is the ratio of I2 by I1 with V2 0. So, this is forward current gain. Forward current gain with output shorted for AC, and finally H22, this is equal to I2 by V2, and under the condition I1 equal to 0, and this we have said that this is equal to HO. So, this is the output admittance, with input open circuited for AC. So, these are the 4 parameters. We should understand their definition, and here the terminal conditions are very important. If terminal conditions are changed, then these parameters will also change, and our analysis will give inaccurate results. So, as we have defined, we have to obtain these conditions to measure these parameters. Now, we move further. So, now these parameters, as I said, they are applicable for every circuit. Now, the input impedance HI, this is again very important in the nomenclature how we express for different circuits. E here, small e, HIE, E means that this quantity is for CE circuit amplifier E, and if we write HIC, this is for common collector amplifier, and similarly HIB, this is for common base amplifier. So, this distinction is to be maintained, and we have to specify that for which circuit we are defining and we are measuring in which configuration we are measuring, because HIE will not be equal for example to HIB, because this will be in CV configuration, this will be in CE configuration. So, they are not the same, because CE circuit is most widely used. So, CE amplifier. So, for CE amplifier the 4 H parameters will be H, I, E, H, R, E, H, F, E and H, O, E. These are the 4 H parameters, hybrid parameters for common emitter circuit. And how we can get the boundary conditions? Let us first express, for example, these two fundamental equations 3 and 4, this equation 3 and 4, we replace these H parameters. So, for a common emitter like here the circuit, this is a signal we will apply, we will measure IB and this will give you IC. This is simplified circuit, just a transistor connected in common emitter, and then these are the parameters. So, this is VC equal to 0, this is the short, because for defining for example these two parameters, the input impedance V2 has to be 0. Similarly, for the forward current gain V2 has to be 0. So, that is to be measured under these conditions, and similarly the two parameters, other two parameters require IB equal to 0. So, this is open, input is open, we apply a test signal here which will establish a current IC. So, this is the open circuit condition, this is the short circuit condition. Now, practically, because how we achieve this in practice, not just by shorting it, otherwise how we will apply the signals. And so, this shorting is achieved by using a appropriate capacitor in shunt. So, AC signal will pass through it without disturbing other things. So, this condition of output shorted is obtained by use of a capacitor, and this open condition is obtained because we have to bias this properly. So, we can't just left it open. So, this open condition can be obtained by using a inductance of appropriate value in series with this. So, use of a capacitor at the output we can establish short conditions, and by using a inductance of appropriate value in series at the input we can establish these open conditions. This is being said repeatedly that H equations are invariant, whatever expressions which we will be deriving, for example, for voltage gain, current gain, input impedance and output impedance, these equations we will be deriving in general, and then we will see that H I B, this represents the input impedance in the case of a common base, and this is certainly not equal to H I E. That means, the hybrid parameters, the same parameter in different configurations, common base, common emitter and common collector, they are different. And we will see that how we can get the value of the parameter in other configuration like common base or common collector, because the manufacturers specify the H parameters only for common emitter, because common emitter circuit is the one common emitter amplifier which is most widely used. This we have been talking, we have been saying repeatedly. Now, before we proceed for the analysis, there are certain thumb rules of the analysis. So, these at least 2 points, let me make it clear that for AC analysis, 2 things we should keep in mind, that number 1, all DC sources have to be reduced to 0, are reduced to 0. So, voltage sources are ground, DC voltage sources are grounded and DC current sources are opened. This is the rule of the analysis, and when of course, when we want what is the effect of this DC, we can use superposition theorem. This is very widely used. Superposition theorem is very widely used in the analysis of electronic circuits, and this we will see when we come to this point. So, this is first point. Another important point is for AC analysis, capacitors. You know that in electronic circuits, capacitors are used in 2 ways. One is as a coupling capacitor. This is the circuit and the signal is applied, this is AC signal through a capacitor. So, this is known as coupling capacitor. Similarly, at the output of the circuit, when we connect the load, this is normally, this is the load RL where we take the amplified signal. This may be, for example, the resistance, the impedance of the loudspeaker. If this is a audio signal amplifier, then the output we will take and that will be this. So, this is connected through a capacitor which is again a coupling capacitor. The other use of capacitor is bypass capacitors. For example, the emitter resistance is often bypassed, so that AC signal goes through this capacitor and we save that drop, AC drop across this resistance Re, because here the drop of AC signal will be a net loss and hence the gain will fall. This we will talk in details later, but this way when the capacitor is used, this is called bypass capacitor. So, remember the 2 ways capacitors are used. These are coupling capacitors and bypass capacitors. So, AC analysis needs, and this is the requirement, as the first requirement was that the DC sources have to be reduced to 0. Similarly, these capacitors are all taken as shorted. capacitors, these are shorted for AC analysis. Now, I give you first some conversion relations. Some conversion relations, that is, I said that common emitter is most widely used amplifier and H parameters by the manufacturer are provided only for the CE circuit, common emitter circuit, but there are the expressions have been derived that we can get without further measurement, we can use those common emitter parameters to get parameters for other circuits like HIB, that means input impedance HI, input impedance in common base is related to HIE by 1 plus HFE. This is, say, it gives a very important information that HFE, as we will recall, HFE, this is the current gain measured under the appropriate boundary conditions, and this is the same beta which we have been talking. Beta is the current gain in common emitter circuit. So, this represents the beta. So, the input impedance in common base is heavily reduced as compared to the input impedance of common emitter circuit. If this is, for example, 100, then this input impedance in common base is reduced by 2 orders of magnitude to that what we will observe in common emitter. So, similarly, HIC is equal to HIE and HFC is 1 plus HFE. This way actually all quantities have been calculated and we can get H parameters for common base circuit and common collector circuit by using H parameters of the common collector, common emitter. Now, I give you the typical values of the H parameters in 3 configurations. So, typical H parameter values. So, here is the parameter and here for CE configuration, CC configuration and CB configuration. If this parameter is input impedance HI. So, here this is having, this is order, mind it, this may vary from transistor to transistor, but to give you an overall idea about these quantities. So, I am giving these typical values 2.5 kilo ohms, while in common collector this is, as I said here, input impedance in common collector is same as input impedance in the common emitter. So, this is also having 2.5 kilo ohms and this is highly reduced, this is 20 ohms only, and the current gain HF this is around 100, this is 101, same as for common ammeter, but this is current gain. You remember alpha in the common base, which is close to 1, but less than 1. So, this is 0.99, and reverse voltage gain which is H r. This is very small quantity, 10 to the power minus 4, here it is around 1, and here also 2.2 into 10 to the power minus 4. And then output impedance is inverse of admittance. So, output impedance, which is 1 by H O, this is around 30 kilo ohms, same here 30 kilo ohms, but here it is much higher, 2 meg ohms. So, these are the H parameters, typical values of H parameters in 3 circuits, and briefly we can see in when we cascade, when we use multi-stage amplifiers, which is very commonly done in systems, then these input and output impedances here, they are drastically different. That means, two common base circuits cannot be connected together because of the large difference in the input and output impedance. You must have done a power transfer theorem, which indicates that from one circuit to the next circuit, power transfer is most efficient when the impedances are matched, but here this is a complete mismatch. Here they are not identical, but order is the same, it is 2.5 kilo ohms, it is 30 ohms, order is the same. So, several common emitter amplifiers can be cascaded without involving a buffer stage, which is kind a transformer stage, which will be required for matching. This much is good enough, they are having similar magnitude, it is not drastically different from matching angle. So, this is additional advantage, plus in common base the current gain is very small. Current gain, as we will see, will enter even in voltage gain. So, here because the current gain is small, so this is another drawback with the common base. Common base circuit is having only few applications in very high power circuits. Now, the hybrid model, hybrid H model, hybrid model for transistor. For example, the two equations are V1, this is H I1 plus H R V2, and similarly I2 is equal to H F I1 plus H O V2. These equations we will be now using, and let us call these equations, and from here this is equation 5 and this is equation 6, and from here we can develop the hybrid model. This is actually pi model, as we call pi model, and let us see this model comes out to be like this. this is inverse of the admittance. So, this represents the impedance. Here is the voltage V 2, the current I 2, here this is V 1 H I and current I 1, and this is a voltage source H R V 2, and this is the current source H F E H F and I 1. Now, how I arrived at this model? The first equation, this we get from the left hand side of this model, pi model. If we use this left hand side, then this is exactly what this equation is. This is left hand side, that Kirchhoff's summation, Kirchhoff's voltage law. For any loop, the summation of voltages have to be equal to 0, or the applied voltage has to be taken as drop at all places. So, this will give V 1 equal to the input impedance is H I. So, the voltage drop here will be represented by the first term, and here this is, as I said, a voltage source which is there because of the in transistor the two junctions do not function in complete isolation. It is very important. What you are doing at the output side also reflects is reflected at the input side. So, this is that reflection, a feedback term. So, anyway, this is the first term in equation 5 and this is the second term. So, left hand side gives you that the equation 5, and this equation, the right hand side, this is summation of currents at a node, summation of currents at a node. For example, let us elaborate this point, that how we get this equation, and this is this right hand side actually represents this equation 6, and this is let us consider just the right hand side and a node, that this is the node, this is the node at a point x, and this is V 2 and this is 1 by H 0, the impedance. Now, this current I 2 will be divided into two branches here. So, this is I 2 B and this is current I 2 A. Then simple summation gives that I 2 is equal to I 2 A plus I 2 B, and I 2 is equal to, this is given by this H F I 1, and at if this is impedance, then what will be the current here? You know that if the voltage V 2 is there, then V 2 divided by this impedance, and that will be 1 by H O. So, H O will come here, and this is exactly what the equation 6 is here. So, we have arrived at the model, and this model is to be used for the analysis of small signal amplifiers, that we will continue I hope you have followed that H parameters, their definitions, and then this is the model which we get on the basis of these two equations, and which can be used for the small signal amplifier analysis that we will continue in the next lecture.